Today we're going to learn about the principle of mathematical induction. The principle of mathematical induction is a way that we can do algebraic proofs. Have you ever heard of the domino effect? Basically, if you line up a bunch of dominoes and you push over the very first domino to fall, it will then cause the next domino to fall, which will then cause the next domino to fall, and this process continues until all the dominoes have fallen. This is really how mathematical induction works. The principle of mathematical induction says we're going to assume that Pn be a statement in terms of n where n is a positive integer. We're going to have 3 steps that we need to follow every time we want to do a proof by mathematical induction. First, we have our base case. This is where we show that our statement is true for n equals 1. Think back to that domino example. If the first domino can't fall, it's never going to push the rest of the dominoes over, so we need our base case to always be true before we can move on with our proof. The next step is our induction hypothesis. This is where we are going to assume that our statement is true for all values of n equals k. Then comes the fun part, the actual induction part of our proof. This is where we are going to show that our statement is true for every positive integer k if we plug in k plus 1. Basically, if we can prove that it will always be true for the following integer, it will be true for every previous integer. We can use our assumption from step 2 in the induction hypothesis to help us prove this step 3, the induction step. The very last thing you should do every time you are proving by mathematical induction is state a concluding statement. These 3 dots right here actually represent in conclusion, so feel free to always write the words in conclusion or thus or some sort of a statement that's signifying that it is your conclusion. And then you want to say that therefore the statement is true for every integer n. Let's go ahead and look at an actual example. Okay, so we're going to go ahead and look at our first example. Our first example wants us to prove that the sum of n integers is going to equal n times n plus 1 divided by 2. That may look familiar from the last week's sections on arithmetic and geometric sequences and series. So we want to actually prove why this works, or that it's always going to work. This is going to be true for all n integers that we plug in. So first, let's go ahead and start by proving that our base case will always hold true. Remember, for our base case, you plug in 1 for anywhere where there's an n because of our statement saying that we're using all integers, so 1 is n. If I plug in 1 for both of these n's in our formula and then simplify, I see that I get 2 divided by 2, which equals 1. It is true that if I sum together the first integer, 1, I would get a sum of 1. I always go ahead and make a check mark next to the base case if it does hold true, as a reminder to myself that it works. The next step to mathematical induction is to write our induction hypothesis. This is when we assume that our statement is true for all values of n equals k. So I'm going to go ahead and write down our induction hypothesis specifically for this proof. We are going to assume that the sum of k integers will equal k times k plus 1 over 2. Again, notice I just substituted in k for n in our original statement. Now, who's ready for fun? We're going to go ahead and do the proof by mathematical induction. We have reached our induction step. Remember, the induction step is when we show that our statement is true for the value of k plus 1. Therefore, what I'm trying to show is that k plus 1 times k plus 2 divided by 2 will actually equal the sum of the k plus 1 integers. Notice how I got these. I plugged in k plus 1 for k, and then I plugged in k plus 1 for k here, but k plus 1 gives me that k plus 2. That's where this statement is coming from. How in the world am I going to prove this? Well, I can use the induction hypothesis where I assumed that this statement was true. The sum of the k integers was equal to k times k plus 1 over 2. Let's go ahead and use that. Well, I know to get to a sum of k plus 1 integers, I am going to first need to have the sum of the first k integers, and then I will need to add that k plus 1 integer. So the sum of the first k plus 1 integers will equal the sum of the first k integers plus k plus 1. But I also know from my induction hypothesis that the sum of the first k integers is the same as k times k plus 1 over 2. So I'm going to go ahead and sub that expression in for s of k, because that is the sum of the first k integers. Now, what's going to happen if I combine this k times k plus 1 over 2 with this k plus 1? Well, before we can do that, we need a common denominator. Let's go ahead and do that. So here I went ahead and rewrote the k plus 1 with a common denominator of 2 so that I can actually combine these two fractions. Now you have a couple different ways you can combine. You could, at this point, distribute this in, and then combine by adding the two numerators, and then factor from there. However, this is also set up perfectly for factoring by grouping. Notice, both our first fraction and our second fraction have a common factor in the numerator of k plus 1. So I'm going to go ahead and combine them, factoring out the k plus 1, and see what I'm left with. Wow! I'm left with k plus 1 times k plus 2 over 2, which is exactly what I needed to prove for the induction step. Awesome job! Remember though, the very last step of a proof by mathematical induction is to state your concluding statement. I'm going to go ahead and do that over here on the right because I have a lot of space over there. So let's go ahead and write our concluding statement. So our concluding statement is going to say that the sum of all n integers will equal n times n plus 1 over 2 for all a sub n equals n, again for all integers, by PMI. This stands for Principle of Mathematical Induction. Now technically, in algebra, this is really the only type of proof that we're going to learn. However, next year, when you get to math analysis or pre-calculus, you're going to learn a lot more types of proofs, and so it's a very good habit to get into to say what type of proof you used when you're doing proofs. Great work.